Okay, so let's go through the solution to example 9.2 from the OpenStax textbook. This example is called the benefits of impulse because it demonstrates how physics can save your life, right? With things like seatbelts and airbags, we're basically using physics to improve your chance of surviving a crash. So let's go ahead and read the problem. A car traveling at 27 meters per second collides with a building. The collision with the building causes the car to come to a stop in approximately 1 second. Okay. The driver, who weighs 860 newtons, is protected by a combination of a variable tension seatbelt and an airbag. So in effect, the driver collides with the seatbelt and airbag and not with the building. The airbag and seatbelt slow his velocity such that he comes to a stop in approximately 2.5 seconds. Okay, so the car is coming to a stop in 1 second, but because the driver is actually hitting the airbag instead of hitting the wall, the actual collision for the driver is actually taking longer. It's 2.5 seconds long. In part A, the question is asking about what is the average force that the driver experiences with the airbag. In part B, take away the airbag and the seatbelt, and in that case, the collision time decreases to 0.2 seconds because this time he stopped by the steering wheel instead of by the airbag, so the collision happens a lot faster. And the question is, what force would he experience in that case? Okay. And so when we see a problem like this, well, they told us a hint about how to solve the problem in the name. They said impulse, and impulse is the way we want to solve this problem because impulse relates force and how long that force is applied for. Right? In this case, they tell us how long the force is applied for. They don't tell us the force. But luckily, we have another equation for impulse, which will allow us to solve for the unknown. Right? So conceptually, let me use a different color here. Conceptually, impulse is the integral of the force as a function of time. But it turns out we can also rewrite this in a different way. Impulse is the average force acting on an object times the time in which that collision occurred for, or in this case, how long the force was applied for. And in general, impulse is a vector formula, so we have to use vectors here. And so this is our unknown, the average force experienced by the driver. And we know the time, we know how long the collision occurred for, so we have, our unknown equation that this is probably a good equation to use. Okay. The only way to solve for this, though, because we don't know the impulse, it's not given to us in the problem, luckily we have another equation for impulse. The secondary equation for impulse is that the impulse is equal to the change in the momentum of our object. Right, so this is conceptually what happens. If you apply some net force over some period of time, you're going to have some acceleration over some period of time, and your velocity is going to change, and therefore your momentum is going to change. And so this is the relationship that we actually derived earlier, right? That the change in the momentum of the object is equal to the force applied times the time in which that force was applied. And so in this case, we're going to be able to find the impulse using this equation, because we know the momentum before the collision, we know the mass of the person, and we know the velocity of the person before the collision. After the collision at time 2, we know the person is at rest, so the momentum is 0 after, and so that will allow us to find the impulse. And then once we know the impulse j, we can use this formula to solve for the force because we know the time. So that's conceptually what we're going to try. Also a little bit conceptually here, just why is the seatbelt going to save this person? Well, I could think about impulse using this definition. If I plot force versus time, if I extend the period in which I have a collision, basically that would extend the amount of time, so I could draw a plot like this. Right? The force is going to be some complicated thing. If I was to attach a force meter to a crash test on me, it wouldn't be some constant force. It would be some complicated force. But luckily with impulse, we can solve for the average force. And the impulse here is going to be the area under this curve. Okay? If I was to instead take away the seatbelt, I would have exactly the same impulse because the change in my momentum would be exactly the same, but in this case, the time would be much smaller. Now it's 0.2 seconds instead of 2.5 seconds. So now I have to draw a line that has the same area in a much shorter period of time, so I end up getting something, like this, some very large force applied over some very short period of time. Both of these curves could have the same area, they have the same impulse, but in the blue curve has a much larger force. And so that's what we want to avoid. by having seatbelts and airbags, which extend the amount of time in which a collision occurs. Okay, so now we've kind of introduced the idea. Let's go ahead and try to solve this. So in part A, they tell us the time in which the force is applied, the time of the collision of the person with the airbag and seatbelt is 2.5 seconds. And as we conceptually talked about earlier, we can calculate the impulse using our blue definition here. It's P2 minus P1. Impulse is a vector, but let's just say all this motion is in the x direction. In that case, this becomes just the impulse in the x direction. We can talk just about the x component is equal to the momentum of the person after the collision in the x direction minus the momentum of the person in the x direction before the collision. Okay. After the collision, the person has stopped, so that's just 0. And so the impulse just becomes equal to minus the momentum of the person before the collision, or minus the mass of the person times the velocity of the person before the collision at time 1 in the x direction. Okay, we know the velocity is 27 meters per second. We don't know the mass of the person. They told us the weight of the person is 860 newtons. So if I know the weight is equal to 860 newtons, I can set this equal to mg because I know that that's my formula for weight, and I can solve for the mass, which would be equal to 860 newtons divided by g, 9.81. I'll just use 9.8 like the book does, 9.8 meters per second squared, and therefore the mass is equal to 87.8 kilograms. Now that I know that, I can solve for my impulse. My impulse in the x direction is going to be equal to minus the mass, which is 87.8 kilograms, times the velocity before the collision, which was 27 meters per second. And so I find that the impulse in the x direction is equal to negative 2,370.6. And the units here are kilogram meters per second, which is also our unit of momentum. Okay, so we know the impulse. That's the same no matter what for this collision, because it depends only on the mass of the person and the initial and final velocity. So it doesn't matter if we have an airbag or not, the impulse is the same. Okay, now that we've used the blue equation to figure out our impulse, we can use the green equation to calculate the average force, right? If we use this equation, and again just go to our x component of our impulse, we can find the average force in the x direction using this, right? So therefore the average force in the x direction is just equal to the impulse in the x direction divided by the amount of time in which that force was applied. And so I can just plug in at this point. This is negative 2,370.6 kilogram meters per second divided by the time for this collision, which was 2.5 seconds. And when I plug that all in, I find that the average force in the x direction is equal to negative 948 newtons. Okay, so that's our answer. Let me just highlight that for us so I can point it out later. So our answer for part A is negative 948 newtons. So that's a pretty large force. It's more than this person's weight, but it's just 1.1 times the person's weight. It's just a little bit more than the person's weight. So it's a big force, but it's not. The person's going to live, right? So luckily we have airbags and seatbelts. In part B, we're now going to solve the same problem without seatbelts. So the collision is going to occur much faster. It's now going to occur over 0.2 seconds. That's how long it's going to take for this person to go from moving 27 meters per second to being stopped. Okay, so to solve that, in part B, I can use exactly the same formula we just derived. And the impulse is exactly the same because the momentum change is exactly the same. They're still going from 27 meters per second to 0. And so the only thing that changes is our denominator here. So this is again equal to minus 2,370.6 kilogram meters per second. And this time I divide by 0.2 seconds. So for part B, the force ends up being minus 11,853 newtons. Okay, so that is an absolutely huge force. That's, I think, more than 13 times this person's body weight. So that's a huge force. And so basically this problem is telling us to wear our seatbelt. And let me know if you have any questions on this.